Hey everybody, we're live and in stereo. So now we're going to look into the 2022 set for acid-base equilibria. The first question says, define Bronsted-Lowry acid. What is an acid? We already know that a Bronsted-Lowry acid is a proton donor. So it's a proton donor. Or you guys, if you want to write it in proper English, you guys can say a Bronsted-Lowry acid is a proton donor. Great. Now it says ammonium ion is heated with sodium hydroxide. A pungent gas is produced. That pungent gas is obviously ammonia gas. And we've learned these equations in chapter 4 as well as in O-level IGCSE. I've recapped everything. Remember when ammonium salts used to only react with strong bases, and the reason for that we already know is that ammonium salts are slightly acidic. So they are going to be proton donors. They would donate proton, and what would happen is sodium chloride would form, salt would form. When ammonium ion donates a proton, it's going to be ammonia gas which would be produced, and then the proton that it donates and the OH minus, it's going to produce H2O. So this is the full equation of ammonium salts reacting with strong bases, right? One of the examples of it. Now it says write the ionic equation. The ionic equation is pretty simple. We all know that if you have an ammonium ion, right? If you have an ammonium ion, obviously this Cl1 minus ion, Cl1 minus ion, they are spectator ions. It doesn't really matter. Sodium ion, spectator ion. It's effectively the ammonium ion reacting with the OH minus ion, right? So the ammonium ion reacts with the OH minus ion, and what does it give you? It gives me ammonia gas and H2O. That's what it gives me, because these in this NaCl, which is a salt, this is a spectator ion, that's a spectator ion, right? So it's ammonia gas which it produces, and it forms H2O. Now if you were to write the state symbols for it, although they are not required, my advice always to students is whenever state symbols are not required, the examiner does not explicitly state it, and the marks are also very evident, it's a 1 mark question, so state symbols aren't required because first of all it's a 1 mark question, and second of all the examiner has not asked it, so you don't need to write state symbols, because if you write state symbols and they're incorrect state symbols, you won't be getting this 1 mark. So don't put yourself in this hurdle of writing state symbols. But those who are interested, obviously these are ions, so these are all aqueous, and water is liquid. Ammonia, you could put a gaseous symbol here or an aqueous symbol here, because obviously it's formed inside the solution, so it will also be aqueous, or you could put gas. It doesn't really matter. But other than this, if you put any state symbol, you will not get this 1 mark for it, so remember this. Next question. It says 25 cm cube of 0.1 molar HCl is added to a beaker and its pH is recorded, obviously, because if it's in a beaker, the initial pH would be, because HCl is a strong acid, the initial pH would be 0 or 1ish, whatever, and now it's being titrated with or ammonia aqueous is being added to it. It's 50 cm cube of 0.1 molar ammonia being added to it. Now because you already know the reaction, it's NH3 plus HCl, and what would it give you? It would give you ammonium chloride right here. The ammonium ion, the HCl, because it's an acid, it's going to donate a proton, ammonium ion is going to form, and the Cl1 minus ion will be left behind. You could also write it like this: ammonium ion and Cl1 minus ion. And what you realize is that this is in 1:1, and because it's in 1:1 and the concentration is also same, we've already learned this in class. The ratio is the same, the concentration is the same. So if you have 25 cm cube of HCl in a beaker, how much NH3 would be required to completely react with 25 cm cube of HCl? It would be 25 cm cube. That's another idea, that he's adding 50 cm cube, but out of this 50, 25 would completely react with this, and the reaction would be over. The other 25 cm cube is just excess ammonia that he is adding, right? And he's saying he's adding it in 5 cm cube portions. The pH of the mixture is monitored until NH3 is all the NH3 is added. So he's effectively adding all 50 cm cube. Now saying HCl is a strong Bronsted-Lowry acid. What is meant by Bronsted-Lowry acid? Again, whenever such questions are, I see there are 2 mark questions. Why? Because first you need to explain acid to the examiner, and then you also have to explain what strong means. So acid is a proton donor. It's a proton donor, and strong means what? Which fully ionizes in aqueous solution. That's what strong means, no? Or fully dissociates in an aqueous solution. Now NH3 is a weak base. Construct an equation that shows the behavior of NH3 as a weak base when dissolved in water. We know that NH3, when it reacts with water, what happens? Because it's a base, it's going to be a proton acceptor. It's going to accept a hydrogen ion and it will become ammonium ion. And what's going to be left behind? H2O gave a proton, so it's going to be left with OH minus ion right here. And does it say include state symbols? No, it doesn't. So Okay, next it says on figure 2.1, sketch a graph to show the change in pH which occurs when HCl is added to NH3. Now we know that inside the beaker HCl is present, and so the initial pH would be somewhere about 1ish, right? 1, 0, 1, 2. The examiner gives you a range, right? So you could start off with 0, you could start off with 1, you could start off with 2, because HCl is a strong acid. Strong acids normally have this pH, and in the curves that we've learned in our classes, we usually start off with 1, right? And what you also appreciate is that it's a strong acid reacting with a weak base, and we've already done so many examples. So you start off with a strong acid and you react with a weak base. What would be the equivalence point? What would be the pH at equivalence point? We already know that, because if a strong acid reacts with a strong base, the pH is going to be 7 at equivalence point. But if a strong acid reacts with a weak base, the pH is going to be more inclined towards the acidic side, right? And so what you realize is it's going to be 7, but you have to use the rule of 2, which we learned. So it's going to be subtract 2 from it, because it's going to be inclined more towards the acidic end. So pH 5 would be your equivalence point right here, and you're starting off with a strong acid. So let's suppose we start off with 0, you could start off with 1, you could start off with 2, it doesn't really matter. So I'm going to start off with 1, doesn't matter, right? And I'm going to start off with 1, and we know from 1 normally we go till 3, and then there's a vertical line, and that vertical line is going to be, where till which point would this vertical line go? Till 7. Obviously when you have a strong acid and a weak base, the vertical line goes from 3 to 7, and we already know that, and we've learned how we calculated 3 to 7. This is an approximate, right? Because if the equivalence point is at 5, we say, hey, go to below this and go to above this, and that would be the length of the vertical section of this titration curve. And then after 7, there's going to be a slight rise to it. There's going to be a slight rise, and then after a slight rise, there's going to be, it would flatten off right before it flattens, right before it flattens right before what? Because NH3 is a weak base, so no matter how much NH3 you add, is going to flatten right before 11. It won't go beyond 11, right? So this is the idea of the entire sketch, and we are going to draw it. And remember, where would the vertical section form? Right here at 25 cm3, because we already deciphered that right here. Although he's adding 50, and we will also add 50, don't worry, because he's added all the NH3. So we're going to add 50 cm3 of NH3, but the vertical section is going to form right here. And this is how you draw all titration curves, right? So let's start. So 1, 2, 3, I'm going to go till 3, and then 4, 5. 5 would be the pH at equivalence point. 7 would be from 3 to 7, that would be the vertical section for me. And 8, 9, 10, 11, just before 11, I'd have to flatten it out. So let's start. You can also start from 0, you could also start from 2, doesn't really matter, right? So let's do this. Oopsie daisies, come on, Suleiman. Let's draw this stuff. And oh my god, my drawing is pathetic, guys. My god, kill me please. Okay, that's fine. Is it okay? Yes, and that's the vertical section now, the vertical section of the graph. You have to draw it with a ruler. I am just handicapped a little. I don't have a ruler right here, so it'll go till 7, and then after 7 there's going to be a slight rise to it. There's going to be a rise to it after 7, and it's going to start to flatten out just before 11, and it's going to go till let's put a slight rise to it. Oh my god, it's killing me. Slight rise to it, and then just before 11 it should flatten out, and the volume of NH3 that you're adding is about 50 cm3, right? So you see, just before 11, I've made sure that it flattens out right here. That's the idea. That's the vertical section, all of that good stuff. And you have to tell the examiner where the equivalence point is. So this fella is my equivalence point right here. This is equivalence point, and you have to show it to the examiner right here. That's it. That's how easy it is to get 2 marks. And let me also show you how books draw it, because my drawing may look good to you, but also I mean, let's add the book drawing. And if you see, this is basically the graph drawn by the books. See, it just flattens off right before 11. After 7, there's a slight rise to it and starts to flatten off right before 11. After 7, there's a slight rise to it, flattens off right before 11. So our graphs, they draw it with mathematical tools. We draw it with our hand. So that's the difference, slight difference, but yeah, that's the idea. Now, in this case, it's using 20 cm cube, obviously, because 20 cm cube would have been the volume of the acid that was required to completely react with 20 centimeter cube of the base, right? Base is being added from the burette, so you might have had 20 cm cube of, it was in this particular question, you actually had 20 cm cube of acid in the beaker, and they were both 1:1, both had the same concentration, so 20 cm cube of alkali or base was needed. So that's the idea. This is how you draw it. So although my drawing is pathetic, but this drawing is far better. That's why I wanted you guys to see it, right? That's it. Next question. The hydrogen halide dissolves in water to form strong Bronsted-Lowry acids. State what is meant by strong Bronsted-Lowry acid. Again, you first of all have to explain acid bit to the examiner and then strong. So what is an acid? It's a proton donor. Strong Bronsted-Lowry acid is a proton donor, which, now let's explain strong, which fully ionizes in an aqueous solution. Done and dusted. Next, on figure 3.2, sketch the pH titration curves produced when 0.1 molar of NaOH is added to 0.1 molar of HBr. That's basically what? Strong base reacting with strong acid. We already know that how we actually calculate it. It's the equivalence point would be at pH 7, the vertical section would be 3 to 11, and after 11, it's going to have a slight rise to it, and it would flatten off just before 13, and because it's a strong acid that we're starting off with, we'll start with pH 1, right? You could also start with pH 0 as up to. And how do you know strong acid is present inside the conical flask, not the strong alkali? Because see, you're adding NaOH from the burette. So if you're adding NaOH from the burette in the conical flask or in the beaker, you're going to effectively have what? You're going to effectively have your acid, right? So other than me drawing it, and where should the vertical section form? It should form at 25 cm cube right here. So here would be where the vertical section would start to form, right? So you start off with 1, move on all the way, NaOH and HBr, right? So you start off with 1, move on all the way to 25 right here, and then this particular at 25 you're gonna have the vertical section right here, from 3 to 11. So this would now become a vertical section right here, and 7 would be your equivalence point, but this should go all the way up to 11 and flattens off just before 30. That's it. That's how strong acid and strong base are going to react. And what should be the equivalence point? Right in the middle of these two, this 7 right here is the equivalence point. Right here, 7, pH 7. Because we know strong acid and strong alkali gives you pH 7. And then now you are in the other case, you have a strong acid and you have a weak base, right? So start off with a strong acid. This is pH 1. I'm going to start off with pH 1. Again, the same 25 cm cube is going to be needed of alkali, right? So 1 to 3, that's going to be a rise to it, gradual increase. Then this is going to be a vertical section, but we know that if it's a weak base, the equivalence point would be where? Strong acid and weak base reaction. The equivalence point would be slightly inclined towards the acidic side, so it would be at 5, and the vertical section would be from 3 to 7. We've already done all of this stuff, right? 2 below it, 2 above it. That's how we estimate it. So 5 would be my equivalence point, and this vertical line would go up to 7. And then after 7 there's gonna be because it's a weak base, it will flatten off right before 11. So there's going to be a slight rise to it after 7, and it's going to flatten off right before 11. Let me fix this. 7. Oh my god, kill me. Oh my god, kill me. You draw it with a ruler, guys. So now it would flatten off right before 11. That's it. That's how it should look. This is my vertical section right here, and at equivalence at pH 5, this is where the equivalence point would be. So equivalence point. Done. And I can even show you graphs from the books. Right. Strong acid and strong alkali graph. Strong acid and strong base graph right here. So in the book, the equivalence point was at 20 cm cube. In our example, it's at 25 cm cube. So that's the idea. You could compare this, the first one, with this one. Obviously we can't draw it as accurately as the book draws it because they use mathematical tools, but nobody cares. And then you have the strong acid with weak base. So strong acid with weak base right here. Let's just take a snippet out. In this case, again, it was 20 cm cube. In our particular question, it's about 25 cm cube. So this is how they look. No, look at the difference. So I hope you guys, who the ones who are good at drawing stuff, you guys can draw it, more accurately than me. And that's it. 2022 set over.